Hi everyone. So let me fix this camera real quick. Gonna wrap up chapter 8 with an extremely fun topic, of course, about experiments. Since I'm an experimental person, right? We're gonna talk about the Hera collider. Oops, over here, Hera. Okay, Hera is like the Greek goddess. That's the hence the reason for the naming, but it stands for the Hadron Electron Ring Accelerator. Okay, it's a weird name if you use it in physics language, but then people just call it Hera because it's easy to remember. And and there's actually an experiment here called Zeus. Oops, this is not going to show up on the here, right? Then so they're really into this Greek god thing. The other experiment that's actually on here is actually called H1. So yeah, who knows why that's just happens to be there. Okay, so what is Hera? Hera is a collider that ran, I think, up to 2007 before the LHC turned on. And basically what they did is they collided electron and protons together. Actually also positron. They collided basically electron or positron together. The energy of the electron or positron goes up to about 28 GeV, so not very high energy in today's standard at least. The proton can go up higher energy because since the proton has a higher mass, it'll lose energy less as it travels through this ring. The proton's energy is about almost a TeV. I think they first started at 820 and then they were able to upgrade it to about 920 towards the end. Okay. If we were to calculate the Q square of these collision, the Q square will be about 20,000 GeV squared. So be careful, like this is GeV squared. When you're calculating this thing, you should take the square root of it, just so that we know kind of the magnitude of the momentum transfer. Okay, with the center of mass energy of about 300 GeV. Okay, so that's basically the square root of S number that we always calculate. Okay. If I remember right, I think this ring is about 6.5 kilometers long. So that would be about 1/5 the size of the LHC, which is, so this one is in Germany. It's in this lab called DAISY. I actually don't remember what DAISY stands for. It's like Deutschland Electron Synchrotron, and the Y, I guess, goes with the synchrotron collider. Okay, or the Large Hadron Collider, which is the one that's currently running, is partly in Switzerland, partly in France, and it's actually, I think, 27 kilometers long as opposed to 6.5. So is the so they're able to reach much higher energy. Okay. The Large Hadron Collider, however, cannot accelerate electrons or positrons. It can only accelerate hadrons, meaning protons. Sometimes they could do gold atoms. Sometimes they do lead atoms, not atom, lead nucleus. Okay. But we're here to talk about Hera because Hera actually spent about 26 years it was running to basically measure these parton distribution functions that we've been talking about this whole chapter. Okay, the two primary experiments on Hera, right? The first one is called H1. Here's a little picture of it. This is just the outermost part behind these cement blocks, right? Inside here, the beam is coming in here and coming in here and actually colliding behind the cement block. Okay, and then I'll show you an event display in a second here. Okay, the other primary experiment is called Zeus. Okay, this is actually Zeus partly being taken apart, so you can see the rails here where they're sliding the whole detector open so that they can take it apart. Okay, we don't have to talk about the detail of which of these particle detectors are. Those of you who are going to work on Atlas will get to learn basically the next generation version of this. So we're not going to talk too much about Zeus and H1, but they are in a similar design as the current detector at the LHC, which are the CMS and Atlas. Okay, so let's look at And just to note that the reason they turned off in 2007 is because the LHC turned on in 2008. So, basically it made the Hera collider kind of obsolete in a lot of ways, because the LHC is able to probe higher and higher energy, and they really already took a lot of data on these electron-proton scattering already. Okay. So speaking of Hera, electron-proton scattering, so the way that Hera works is that you shoot an electron, well, maybe not one electron, probably like 10 billion electrons into a beam, and then 10 billion electrons, protons, coming the other way, and they basically smash into each other. Okay. Since the proton will have much higher momentum, 820 GeV, and this one will only be about 28 GeV, most of the stuff that comes out is going to go along one particular direction, meaning along the direction of the proton. Okay, so that's why the detector is designed so that it detects the stuff. They don't expect to have anything coming out here. Most of the stuff actually comes in this direction. Okay, and basically from just measuring, tracking all these particles that comes out during these collision, you can actually measure, right? What's the cross section, for example? What's the rate, right, of events that's coming out at a particular angle? So this one doesn't really show it that well. Let me show you another one. Okay, so this one is from Zeus. Okay, so same thing here where you have the electron coming in here. Let me pick a better color. All right, electron coming in here, and then the proton coming in here. Right, what happened is that the scattering happens, and then basically you have a couple of things come out. So maybe this is the angle, probably the other one. This is the angle that the electron came out. So you can actually figure out what is the energy of the initial electron. And then if you know the scattering angle, you can actually calculate, for example, E3, right? This is the nomenclature we usually use. You can also measure what's coming out of the proton side, where this will be actually P4 in our nomenclature. You can actually measure what's basically by the cone side of this thing, measure the mass of the thing that came out. Okay, all right. These event displays is provided to us for the Zeus experiment. There's actually a paper written about this, so making event display is really important. That way, we can see a picture and understand actually what's going on. Okay, but let's look at the data, specifically the one that the book found, which is actually very, very illustrative. Okay, so in this section, the book actually shows you this data where I think this is a combination of H1, Zeus, BCDMS. So these are other experiments. Okay, and then the triangles are as slack, so those will be the lower energy guys. Okay, and what they did is they basically collide these things together. They collect the particle that comes out at all these different angles. But if you know which angle that these particles come out of, right, it's going to be azimuthally symmetric because you don't have a preference in that direction. But if you have a particle, let me draw this instead, okay? If you have a particle, right, that comes out, you have an electron comes in, and then proton comes in, right? And then the electron goes off in this direction, right? You know exactly what the theta is, and then you probably have a bunch of stuff coming out over here with the proton, right? You can actually constrain what, the E1, E2, sorry, well, E1 from the energy of electron, right? What is the Q square, right? What is the X, right? Q square, X, and Y, right? I mean, if you want, you also can, calculate mu, but this mu is actually dependent on X and Y anyway, right? So with that, what you can do, right, is for each of these particular Q square, X, and Y, put them in different piles, okay? In this case, what they're doing is that, they pick out, let's pick this one down here, right? It's kind of isolated. they pick up events that, oh, it knows it has an X of about 0.85. So 85% of the momentum of the proton is actually carried by the quarks. Okay, right? So in that case, right, what you can do is then, well, you can plot this as a function of q squared, right? And then you have this trend, right? This kind of slowly decreasing trend on a log scale, okay, right? And what this refers to is basically what the structure function is telling you, okay, times 2 to the ix, which is actually, basically this is actually f1, okay? Doesn't matter if it's f1 or f2, but because they're dependent on each other anyway. But right, the idea is that you are able to plot this. You're able to make this plot by comparing how many events are you getting at this particular. You're going to convert from this angle, this E3, right? Convert these variables into q squared and x and y, okay? And then now, right, you put the events that have a particular x in a little box, make a plot out of it, right? And then you got these, 10 or so data point down here, okay? And then you have a different bin with a different x, right? You plot these, right? And you do the same thing, blah, 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 blah. So you have all of this with different x, right? Different momentum carried by the quarks, okay? And then you can make this as a function of q squared, because once you determine theta and E3, you can also calculate what q squared is, okay? And then you plot this as a function of q squared, and then now we're going to interpret what this means, okay? So, notice that the bulk of these lines are fairly horizontal. I would say go up to here, right? So this is horizontal, okay? Right? So when you make a plot, and whatever you're plotting against, let's say you're making a plot of, right, y versus x. Let's not use x. Let's use another variable, alpha. Also a bad variable. Well, I'm going to use x, right? If you have a straight line like this, a flat line like this, that means, right, the function does not depend on x, right? So this is showing you that, right, for most x's, okay, meaning most momentum, in most cases where the momentum is carried by the quarks, well, somewhere between 0.1 to about, 0.01, 1% to 0.4, 40%, right? Basically, the rate that you're getting these events, and therefore this structure function f2 doesn't depend on q squared. You have a flat function, okay? So this is, right, what's known as the Borkin scaling argument. The Borkin scaling, right? Where basically what you're doing is you're scattering off the individual quarks inside the proton, and therefore you just have a cross section for each of those individual quarks, and it doesn't depend on the q squared between the doesn't depend on q squared, because you are at the wavelength where you are scattering off all, the individual quarks, okay? All right, so that's that little middle bulk here, okay? Let's deal with the other part where you have this high x situation, specifically high x and also high q squared. So what's going on there? Okay. What's going on there is that the momentum transfer between the electron and the proton, right, or the quarks inside the proton, right, what's happening there is that the energy is so high that what's happening is that you're running into the strong coupling constant changing on you as you increase this energy. Okay, it's actually the strong coupling constant actually decreasing in high energy. And this is going to be, we're going to run into this when we talk about the strong interaction next module, which is going to be 2 chapters. We're going to jump chapter 9 to jump to chapter 10. But what we're going to see is that as we increase the momentum exchange into interaction, the strong interaction actually gets weaker and slightly strong as weaker, as in slightly weaker than the strong interaction as it goes down. And this is why this is actually have a downward trend as you go to higher and higher Q square with these high momentum transfer, momentum fraction carried by the quarks. Okay. What about the other end? Let's do that in blue, right? What about this stuff up here? Why is this trending upward instead? The reason this is trending upward is that at very, very low Q square, okay, right, you are back to basically scattering off of the entire proton as opposed to the individual quarks inside the proton. Okay, so that's why you're gonna, I mean, if we actually are able to complete this plot, right, we actually have this kind of like, you know, downward hill, this little hill situation. Okay, so in general, okay, this is known as scaling violation, meaning it doesn't, this Bjorken scaling is no longer true. It's only true when you have a X of between about 1% to about 40%, and then the Q square, right, is, you know, somewhere between 1 to maybe like 100,000 GeV square. Okay. So Thomson tried to illustrate this where, you know, if you were thinking about this F2 structure function, right, if you plot it as a function of Q square or log of Q square, right, if you will have high fraction of momentum carried by the quarks, then you will have this downward trend. If you have a low amount of momentum carried by the quarks, then you have this upward trend. And then, you know, somewhere in the sweet spot, you have this constant where you have this medium momentum carried by the quarks, and then you have this flat distribution, which allows you to use this thing called the Bjorken scaling, where while your cross-section doesn't actually depend on Q squared because you are just scattering off of the individual quarks. You're at exactly the right wavelength of photon being exchanged between the quarks and the electrons so that you don't have any dependence on the Q square anymore. This this right plot here is trying to show you the other argument where the strong interaction gets weaker as you go to higher energy. Okay, so high Q square, right? The structure function tends to push towards the left. Okay, where at low Q square, the structure function actually pushes towards the right. Okay, so that's what we're trying to show here. So all this is fairly complicated, and you know, we have to make, so since there's no analytic solution to this, we can't just write the equation. All these parton distribution function as model using this DGLab. Okay, I just pronounced it DGLab. I actually don't know what the names of all these different people are before this class, so I'm not even going to try to pronounce them, right? Because I may, you know, say a bad word if I try. But right, if you look up parton distribution functions for, you know, protons and neutrons, you are going to run into this DGLab model. Okay, what this DGLab model allows you to do is basically it plots the fraction of each, the momentum carried by each type of quark as a function of Q square, and with this basically as a function of x, where is the momentum carried by it. Okay, so let's examine this plot very carefully. Okay, so let's do the simplest one. Okay, so let's do this one, right? X of the momentum fraction carried by x times v, sorry, uv, right? This v here stands for the valence quark, right? So it's the valence up quark. Okay. So what this says, this is plotting, right, this curve here. So it changes with different x's. You also have a different curve if you have a different q square. Okay. And what you can see here is that it kind of peaks, right, at about, 1/3. Okay. Okay. And then you see a similar thing for the down quark, actually going to peak at about 1/6. Okay. Okay. Right. And then you have these things called the C quarks. So these are the stuff that's, the virtual quarks in there. You also have a little contribution from the strange quark, which we haven't talked about yet. So let's just ignore that for now. Okay. But the important thing is that at lower and lower x, right, very low fraction of momentum carried by the quarks, guess what's going to happen? Most of the momentum is going to be carried by the gluon. Okay, this big sea of glue that that's gluing these up and down quarks together. That's actually what's carrying most of the momentum. Okay, so most of the you can interpret this as most of the mass is actually carried by of the proton is actually due to the gluon and not due to the quarks inside. In fact, we know this because the mass of these quarks are something on the order of few GeV, right? Right. The mass of a proton, right, is 900. Sorry, few MeV, right? The mass of the proton is 938 MeV. So the mass of the proton is 930 MeV, where the mass of the individual quark, right, is about, well, the up quark is 2.4, right? Even if you multiply that by 2, you're going to get about 5. The mass of the down quark is actually about 5 also. So only 10 MeV of the mass of the quarks is actually out of the 938 MeV is actually carried by the quarks. The rest is actually gluons and C quarks, right? That's being created and destroyed by the gluon. And so therefore, this is the reason why you see this distribution where a lot of the momentum at low x, okay, is going to be carried by the gluons. Okay.